So today we'll be discussing conservation of mass of a fluid, and we'll see how it can be written down, and in some cases it will help us uh, draw the plot the velocity, calculate the velocity fields in an easier manner. So we'll see the consequences of this equation. And of course, this is the first conservation of mass equation. And later we'll be discussing the conservation of momentum equation, which is the actual Navier-Stokes equation. And in some conditions, we don't need to explicitly write down the energy equation. But for compressible fluid flow, we'll see that the energy equation also becomes important. Uh, Not for non incompressible flows, and why and therefore we shall of course discuss. But starting to discuss about conservation of mass, suppose there's a volume V of fluid. So volume V of fluid, and within that there is a fluid density of rho F. This volume and the boundary at the moment is absolutely fixed in space. And in that case, the surface element of the surface is fixed in space, this volume is fixed in space. But suppose there is fluid flow out of this volume through this surface, then the mass inside this volume will change. And what is the rate of change of mass with time over volume in volume V? Well, suppose here the fluid is flowing out in some random direction, in this direction, then the flux of fluid through a small surface area element is V dot uh, n. N is the normal vector, is the normal of the surface pointing outwards. And basically you have to take the dot product. If velocity is in this direction, then the flux is like, you take the component uh, normal to the surface, and the minus sign comes because if the fluid is flowing out, then the mass is going to decrease. Correspondingly, there's this minus sign here. And over the entire surface, if you calculate the flux of the fluid flowing out, so the integral is over S. So dm dt is basically change of derivative with respect to rho f dv, which is the total mass. If you integrate this, and that is equal to the rate of change is equal to the flux of fluid outside the surface. This is the mass current, if you like, right? And then if the volume was held fixed while calculating this, then one can write this dm dt as basically del t, right? Because there's no space dependent, there's no space dependent in this. So hence this part we have kept the volume fixed. We are interchanging the differentiation and the integral. So del rho f del t integral over dv, the volume, by Gauss's divergence theorem, which you must have learned in your first and second year. This surface integral can be written over a volume integral like this, right? And now this equation holds over any element of volume. This equation is independent. We can choose a different volume element, and then also this relationship will hold, except that the volume will be a different volume element and the surface will be a different surface element. But here this is both an integral over volume, and once you choose the volume element, this relationship holds. Hence we remove the integral sign and write del rho del t, rho of fluid, equal to divergence rho f vf. Now if we expand this term so that it's del rho f del t plus v dot grad v, we're just expanding it, v dot grad rho f. And this is essentially yeah, the other term we have just expanded it. Then a combination of these two terms right, give the so-called convective derivative. What's the difference? Now, suppose as the fluid element is, if the fluid is flowing and the volume element itself is changing shape as a function of time. So that is then basically uh, that itself is now within this convective derivative, right? So v dot grad f, and at the different points there is different density as well. So that is incorporated here. This is so basically this convective, this space dependence has been uh, incorporated here, and then rho f divergence v equal to 0, right? And however, as the fluid moves, if the density doesn't change, the density of the fluid doesn't change over of the fluid element, then this term is 0. So basically, density of the fluid is constant as a function of time. It's not changing over the fluid element, right? And then what you get is, if this term is equal to 0, the convective derivative of density is 0, then as a consequence, divergence v of f is also equal to 0, because rho f is not 0. But that is only for a incompressible fluid. If you have a compressible fluid, divergence v of f will not be equal to 0. Then you will have a finite value of del rho f del t, and as a consequence, uh, this will not be equal to 0. On the other hand, whenever you see divergence of vf of velocity field is equal to 0, you know that you have a incompressible fluid. That follows from this, right? If this is 0, then this term also has to be 0. Now you know that gas is of course compressible, and liquids is also very slightly compressible. If you give huge amount of stress, you can compress a liquid, but we'll show you later in the course that as long as the velocity of the fluid divided by the velocity of sound in the fluid. The velocity of the sound, I should remind you, is related to the compressibility of the fluid, right? If you might have seen the formula, but how it comes we'll discuss later. If the velocity, if this ratio, velocity of fluid by velocity of sound in the fluid, is much lesser than 1, and this ratio is a dimensionless number called the Mach number. You might have heard of the Mach number when the plane is moving compared at speeds comparable to the speed of sound in that medium, right? And and then you can talk of well, the plane is flying at zero point 0.5 Mach, and fighter jets fly at, I don't know, Mach 1 and Mach 2 and so on and so forth. So that's the Mach number, the velocity of the fluid and ratio of to the speed of sound in that medium. If that is much less, then basically any flow, that flow can be considered as essentially an incompressible flow. Um, why, as I told you, we're going to learn later. But right now, let us study the consequences of incompressible flow, and then we'll see under what, I mean, how under certain conditions one can approximate a fluid flow to be incompressible flow. So we can, under certain conditions, if you have incompressible flow, under certain conditions, when we have incompressible flow, uh, it allows us easy calculation of flow fields, but only if the flow is of 2D, is 2D. There's no third dimension dependence. Then one can define something called a stream function, which is a scalar field, and it's always easier to work with scalar fields. And why is that? Why can we define a stream function? So remember, what are the conditions? Incompressible flow, no volume dilation, and it has to be 2D, and the flow is 2D. Uh, so the condition for incompressibility is divergence of Vf equal to 0. And if the divergence is 0, then the velocity field can be written as curl of a vector field, right? Because divergence of a curl of a vector field is always equal to 0. So basically, instead of solving for the velocity field, you can solve for this potential vector potential field, but that's not very useful because anyway you are solving for a vector field, and you are now have to solve for another vector field. So there's no simplification of the problem. So except in one condition, one can adapt it to a more simpler case. It's more useful to solve for a scalar function, and that will be possible uh, when the flow is 2D. And why is that? Because suppose there is no explicit dependence in the third direction, the z direction, it's a 2D planar flow, then you will have del v. There is no component of velocity in the z direction, right? It's identical. There's no component of velocity in the z direction. Then you can write del v x del x plus del v y del y equal to 0, which is a consequence of this divergence of Vf equal to 0. And now you know that if you write Vx to be some scalar field and y derivative, if you relate Vx to be del y of a scalar field psi and Vy to be a minus del x of a scalar field psi, then you can see that by substituting instead of Vx, I'm writing del psi del y, and instead of Vy, I'm writing as del psi del x. Then essentially this relation will hold true trivially. And then now you can define a scalar field and solve for the scalar field. And once you have got this function psi, you can just take, which is a scalar potential, much easier to solve than vector. So once you have got this, using boundary conditions, forces, whatever, which we have not discussed now, but suppose you have solved for a function psi, then you can take the suitable derivatives with respect to y to get Vx, and the suitable derivative with respect to x with a minus sign to get Vy. You get your velocity fields, right? And you can trivially check that in this case, if you have a scalar field psi, if you can define something called the stream function, this psi is called the stream function, then your A vector field, this A vector field will be 0, 0, psi. You can just take the curl of it and you'll see that you'll get your Vx and Vy, right? So that's why it will be. So you can just check for the curl. If you have, you'll get Vx and Vy, right? And of course, just to remind you, because you are using this, incompressible fluid is important. And since you are writing Vx as a derivative of a scalar function, you need the flow to be 2D, right? Then you can define something called a stream function and use that to calculate your velocity fields, right? So this is what I have already discussed. I have already emphasized this multiple times, including the z component to be 0. Uh, Now you can also write the velocity fields in cylindrical coordinates. In that case, uh, basically, uh, if you have a planar flow, I mean, right? Then if z component is 0, then you can write v rho uh, to be del psi uh, del phi, right? It's the same principle. Basically, you look, uh, see, because then if you take your divergence, you have to write down the expression for divergence. Is if you define like this, then again you will always have this condition will be satisfied in the cylindrical coordinates. But in this case, now the v rho will be defined as 1 by rho del psi del phi, and v phi will be defined as del yeah del rho, and this is del phi. Now the thing to note is that the velocity field at any point dot grad psi, the direction where psi is increasing at the fastest rate, this is identically always equal to 0. And what is the reason? If you just substitute the Vx components, so this is Vx, right, into del psi del x, and this is Vy, this is Vx, this is Vy, and then you can trivially see that this relationship is equal to 0. And this means that this velocity field is always perpendicular to grad psi, right? So basically this velocity field is perpendicular to the maximum to the direction where psi increases uh, at the maximum rate, grad psi, uh, and that means basically that velocity field, this v vector, must be tangent to the curve psi equal to c, right? Because basically when along the curve, the psi is the same direction, perpendicular to that is grad psi, which means that psi equal to c constant, right? The lines along with psi equal to constant and perpendicular to that is the maximum rate of change of psi. So psi equal to c is essentially the direction of the streamlines, right? Because remember that if you take tangent to the velocity of, so v essentially is basically is along the tangent into the is the local direction of flow. Right? So this must be tangent to the curve psi equal to c. So that's the reason that psi equal to c will be the streamlines, right? So that's one interesting consequence. Now, what we'll do is basically see if we have different kind of streamlines, sorry, the stream functions, what kind of velocity field does it correspond to. So we'll just take a general form. So of course you have to solve from different boundary conditions and etc to get your stream function. But once you have your stream function, and suppose its functional form is something like this: ax square plus by square equal to constant, then by taking suitable derivative with respect to y, you get vx equal to 2by, and taking suitable derivatives with respect to x with a minus sign, right? This is the stream function, you get minus 2ax. And because these are the two formulas, right, that's what we derived here. That's what we derived here. Uh, and now we are going to look at special cases. Now, suppose a by b equal to 0, which means that b is finite by a equal to 0. Then what you have is essentially, so a equal to 0, you are taking the derivative with respect to y to get vx, right? And of course, vy will be equal to 0 because there's no x dependence. In that case, Vx equal to 2By. Now, let me remind you, this is exactly what a shear flow field is, right? So if you have psi equal to By square, then Vx is going to be 2By. So Vx is increasing with y linearly. And again, yeah, so it's decreasing. I mean, it depends upon where you choose the origin. Of course, you can shift the origin as well. But if you shift the origin to be in the middle of the flow, then in the positive y direction, Vx is in the positive direction, and in the negative y direction, Vx is in the negative. And this is exactly what is a shear field, and there is a constant velocity gradient. Velocity gradient del Vx del y would be the velocity gradient, right? And that's constant, slope 2b, right? And correspondingly, the psi function, as I said, will be By square, which means that for a fixed value of y, for any particular value of y, psi is fixed. So the streamlines, if you like, are parallel to y equal to constant. Y equal to constant, they are this is the velocity magnitude is constantly changing, but the streamlines all are parallel to each other. The magnitudes are different, uh, By square, but basically, I mean, the lines will be over all times, and they all are parallel to each other, and parallel to y equal to c. So this is the shear flow. This is the stream function on the streamlines for shear flow. Right now, if a equal to minus b, if a equal to minus b, if both have finite value, then the stream function can be written as a square, right? Um, x square minus y square, and take the suitable derivatives, and you'll get Vx equal to 2By, right? Uh, and Vy equal to 2Bx, which means if you look at the y component of V, this direction is the y component of V, the velocity in the y direction, that is gradually increasing as you go ahead in x, right? And similarly, Vx, this is the Vx component, that is again increasing as you go along y direction, decreasing as you go along y direction. Now, what will happen here? Here, you have seen this before, but you know, it has a y component and an x component as a consequence of which, right? So this has a y component and an x component and is gradually increasing. And we saw that this was pure extensional flow, right? So here the flow lines are like this. So you see, it's like this. The velocity fields are like this. The velocity fields are like this. But here you have both x and y, and correspondingly the velocity, the streamlines are along this. And remember, as we saw later, this is extensional flow, and the deformation is exponentially increasing. There's pure compression and pure extension along the principal axis, right? So we have seen this in the past, in the previous lecture. So we are seeing this again. And the corresponding stream function for extensional or elongational flow is something like this, right? Okay. Can elongation flow be realized? Yes, actually, it is used heavily in, especially in engineering, and also to study idealized condition. So what you have is four rollers. These rollers are basically flowing is being rotated. So they're fixed rollers. These red circles are four rollers, and this one is rotating in this direction, this one is rotating in this direction, this one is rotating in this direction, and this in this direction. The consequence, so here we have aligned it so that the principal components of the velocity gradient tensor, when you diagonalize it, they are lying along x dash and y dash. To differentiate between x and y, we are saying, okay, we have to rotate the coordinate axis, and along this you have shear compression, here you have shear extension, and this is a, what is it called? It is called the special stagnation point, I think it is called, right? Now, if you had only by square, as we saw just before, you would have only shear flow, right? So this is how elongational flow is realized, uh, and one does such extensional flow to suppose draw out plates of polymer and so on and so forth. So that's a different topic. So this is just the definition. Now, if A by B was equal to 1, right? So that psi equal to A x square plus y square, right? Then taking the suitable derivative, you would get Vx equal to 2ay and Vy equal to minus 2ax, right? So in this case, the y component of the velocity here is in the negative direction as you go on increasing x. If x is negative, then Vy is positive, and if you plot Vx as you go ahead here, it's increasing here, right? Vx value is increasing with increasing y and becomes more and more negative but higher in value as you go towards decreasing y. And then the flow field that you will get is something, I mean, so this is what I've plotted, this is what I was plotted here, right? If you go along y, if you go along minus x and minus y, and this stream function corresponds to a rotational flow, right? And this will be the kind of stream function. Uh, yeah, so this is the fluid is flowing around. Note, I want to emphasize, soon after one or two classes later, we will be discussing vorticity. So I have just mentioned that this is rotational flow, but you could have rotational flow calculated by the curl of V, the velocity field, which is the vorticity, which can be zero even if you have a rotational flow. Remember, I'm not saying vorticity equal to zero, I'm saying rotational flow equal to zero. As you go on, I don't want you to confuse the terms. Hence, here itself, I am emphasizing it, and later, of course, I will emphasize it when we are talking about vorticity, right? So this is rotational flow. Last case is basically, suppose A is not equal to B, and then psi, the stream function, is ax square plus by square, and then, and this is equal to constant. If you want to look at the streamlines, this is for streamlines, so I'm writing constant here, but that defines the streamlines, because v dot grad psi equal to, yeah, 0. That's how we get this. So in this case, I ask you to check that you can write this as x square plus y square. So this was the streamline. If you remember, for the rotational flow, and this can be written as a shear flow, right? You can check it out. So you can realign the terms such that you have a stream function for pure rotational flow and pure shear flow. Okay, so you can just check it out. And all this calculation of streamlines, etc., is taken from physical hydrodynamics as one example of the other examples give a better conception, hence I'm just doing this. And once you calculate psi, you can calculate your velocity fields. That's, and making you familiar with different velocity fields and velocity gradients, which we were discussing in the last class. So that's what we're doing. Uh, okay. So here I have written down essentially the expressions of grad f and divergence f and curl f and Laplacian in cylindrical coordinates. And with reference to this, you can see that cylindrical, this is a cylinder, and this is z. Uh, if there is no z component of the velocity, then the flow is basically in this plane, right? If the cylinder is like this, suppose this is the cylinder, and there's no velocity component in this direction, then you have flow in this plane. On the other hand, if you have no phi dependence, in cylindrical coordinate, right, then the flow, so this is rho, this is basically the radial direction, right, and z is this. Now there's no phi dependence, the flow will be basically in this plane, if there was no z dependence, the flow would be in this plane for a cylindrical. And you can think similarly in terms of spherical coordinates, right? So for when there is planar flow, there's no phi dependence and divergence v equal to 0, which means that incompressible flow, then this divergence of v from here, you can look it up, becomes something like this, right? And if there's no phi dependence for spherical coordinates, it's just r theta flow again, then it will look like this. And you can adjust and you can choose your v rho in terms of a stream function in cylindrical coordinates, so that this equation always holds true. And you can check it out that if you write v rho to be del psi 1 by rho del psi del z, right, and vz to be del psi del rho, right, then this equation will be identically equal to 0. And similarly, using similar principles, if you choose vr suitably, in this particular case, 1 by r square sine theta, there is r square sine theta in the numerator, so you put r square sine theta in the denominator, and del psi del theta, if you put, then del r and then del theta is what you will have. And correspondingly, v theta, if you choose as, you have r sine theta in the numerator, you choose minus r sine theta in the denominator, and it comes with a minus sign, the sum has to be 0. You choose del psi del r equal to 0, then again this will be exactly equal to 0. So this basically completes at the moment the description of the stream function. Of course, how to get the stream function or the velocity fields with different boundary conditions is a topic which we'll discuss after we have introduced the momentum conservation equation. Okay, yeah, so that's the end for today.